So let's do a quick review. What's everything made out of? Matter. What is matter?
This stuff.
Well, I mean, how did we define it, maybe? Anybody?
Anything that occupies space.
Space and has
Mass.
mass. So it's got some stuff to it. How do we on Earth usually measure how much mass something has?
A triple beam balance.
Okay. And what are we recording with something like a triple beam balance?
Weight.
We're recording its weight, right? So, is weight truly mass? Are they the same things?
Yeah.
No, weight has to do with mass. Which one is constant everywhere in the universe at all times?
Mass.
Mass. Which one varies?
Weight.
Weight, what does it vary by?
Gravity.
Gravity. You have more weight on Earth than you do on the moon, but your mass is consistent. Matter. Generally speaking, the smallest whole unit of matter that everything else is made up and has all the constituent parts is called an atom. Right? What's it made up of? Neurons,
Electron.
electrons, protons. Where would I find protons? Nucleus. Where would I find neutrons? Where would I find electrons? Out there in the shells, the clouds, the orbitals, whatever words we want to use there. What's the charge on a proton? Positive. What's the charge on an electron? What's the charge on a neutron? Neutral. Okay. Opposites attract. Electrons go around protons. Fun fact, I don't remember if we covered it or not, but if an electron for some reason crashed into a proton, what would it form? Form a neutron. Those positive charges would cancel out. The difference in mass is basically negligible, and a proton becomes a neutron. Conversely, if a neutron lost an electron, it becomes a proton, right? It's radiation, beta radiation, actually. So, okay, matter exists in 4 primary forms. What are they? Or states. Solid, liquid,
Plasma.
gas, plasma. Solid, liquid, gas, plasma. So I move from a solid to a plasma. What's true of the matter? Has more energy. Anything else? Which ones have no, which one is rigid? Has a definite shape. Solid, okay. Which one has a definite shape so long as it's in, which ones have definite shape so long as they're restrained? Liquid, plasma, gas. Which one has just electron, or excuse me, has atomic nuclei with the atoms, or at least a number of their electrons stripped off? That's plasma. Okay. Which ones are flowing?
Yeah.
Gas and
Liquid.
and plasma. Okay, good. All right. Make sure you know your chemical properties and your physical properties. Right? Do the properties change if the state of matter changes? If I go from a solid to a liquid, does water change? Is it still water?
Still water.
Sure it is, right? It's gained energy, it flows more freely, or it flows freely now, but it's still water. But now if I start doing things with electrons and recombining them, reconfiguring the individual atoms,
Yes.
what kind of change is that?
Chemical.
It's a chemical change. What happens in a chemical change?
New bonds are formed.
New bonds are formed. What do we call that? What's happening in a bond?
Reaction.
We're sharing
Electrons.
electrons. Okay, good. If I have a chemical reaction, do I ever lose mass or gain mass in my chemical reaction?
No.
If I had a balloon filled with hydrogen and a balloon filled with helium, and these are very special balloons so that when I have this reaction, it does not cause the balloon to disintegrate or pop or burn. and I put them together and they react and I get water. If I had 10 grams of hydrogen and 5 grams of oxygen and I put them together, how many grams will I have of my new stuff? 15. The law of conservation of matter. It's neither created nor destroyed. All right, that's probably about where we got to, don't you think?
Yeah.
Yeah. Okay. Well, oh, I'm sorry, I take that back. I'm sure we talked about this a little bit. Did we talk about intensive and extensive properties?
Yeah.
Yes.
Okay. So which one depends on how much of the substance I have, intensive or extensive? Intensive or extensive, those are my choices.
Extensive.
Which one depends on how much of it I have? Extensive. Name an extensive property.
Volume.
Volume,
Mass.
mass,
Length.
length, height, width. Okay, good. Name an intensive property. Independent of how much of it I have.
Melting point.
Melting point,
Color.
color, freezing point. Good.
Conductivity.
Okay. Then we talked about classifications of matter. So we had this concept of a pure substance. What do you think of when you think of the word pure?
All the same. It's like all the same.
All the same, completely unmixed. Okay. In Isaiah it says, "Come, let us reason together. Though your sins be as scarlet, I shall make you white as snow." What is Isaiah saying there? What is the Lord saying through Isaiah there?
Can you repeat it?
Though your sin, come, let us reason together. Though your sins be as scarlet, what color is scarlet? Red.
Oh, okay.
I will make you white as snow. So, if we had a white carpet in here, and somebody were drinking grape juice or something, or had strawberries and spilled it all over, it's going to become stained, right? Will it be a pure white carpet anymore?
No.
No.
No, right? Because there's now at least two things mixed together. Will it be a pure red carpet?
No.
No, because it would have to be just perfectly uniformly red. That's the concept of purity, is it's only one type of thing and it's that thing through and through, okay? So as we're talking about a pure substance here, we're saying it's one thing consistently, completely, hence the word homogeneous, completely unmixed, okay? This contrasts with like a mixture, right? So instead of a homogeneous thing, maybe we might have a heterogeneous, which is, by the way, what does homo mean? Same, and hetero means?
Different.
Different, other, okay. So we would have different things. Did we talk about milk last time?
Yeah.
Okay, so they would shake that stuff up to make it homogeneous, but on its own, it would not be that. It would be heterogeneous. It would split into different layers. Okay. What is an element? Yes, no, maybe so. Name an element.
Iron.
Iron, name another.
Sulfur.
There's silver and sulfur in there.
And copper.
Copper, yeah.
Gold.
Gold. What's true of gold? The element gold. It's always gold. Gold is never going to be silver. Gold's always going to have the same properties, right? It's going to have the same melting point. It's going to have the same conductivity. It's going to have the same reactivity. Gold is never going to be silver, right? Silver is never going to be gold. People used to try to do that, and maybe they still do. They're nuts. People used to try to turn one metal, especially some cheap metal, into something like gold. You ever heard of that?
Yeah.
Called?
Alchemy.
Alchemy, right? They did learn some cool chemistry along the way, but you know, that can't be done. Of course, they didn't know that. All right, element, molecule. Molecules are going to have two or more, what? Atoms that are
Bonded.
bonded together. They're going to share some electrons. That's good. So a bonded collection of two or more atoms of the same or of different elements. And then a mixture. Mixture can be separated without breaking chemical bonds, right? If I have salt water, can I separate salt from water?
Yes.
How?
Boil it.
Huh?
Boil it.
Boil it, right? Distill it. If I boil it, I'll lose it. But if I distill it, I can collect it, right? You can do that. If I If I went and got sand and brought it in here, can I separate like the iron that's in that sand from the rest of it?
Yeah.
Yeah, what do I need?
Magnet.
A magnet, right? So mixtures like this can be separated usually using just regular physical means, methods. Okay? All right, and we've talked about homogeneous, we've talked about heterogeneous, and we talked about even measurements, precision and accuracy. Which one, don't look, which one says, hey, I'm going to get very near precise and accurate. If I am scattered everywhere, I am neither. If I've got a bunch of them in a tight grouping, but they're not on target, that's precise. If I get kind of close to the bullseye, but they're not very tight, that's accurate. Good. Okay. All right. SI units. Standard International. Comes out of the French Revolution. You don't need to know that. I don't care that you know that. But maybe it'll be useful on Jeopardy one day. So, Scientific International. These are standardized things. In my astronomy class, I got a bunch of kids or a bunch of young men from other countries, and it's great because they speak this language, like centimeters and kilograms, and we're over here talking about feet and pounds, and those are very imprecise things. It's not very systematic. How many inches in a foot?
12.
12. How many feet in a yard?
3.
How many yards in a mile? I have no idea. Right?
4,000 something.
Couldn't tell you. Whereas with them, everything is a base 10 system, and it certainly is with the SI and with the standard notation there. So, or scientific notation. So let's look at this. We've got, well, let's talk about meters. Approximately, how big is a meter?
2 yards.
No.
No, it's a little bit more than a yard.
Yeah, it's about roughly a yard. Okay, roughly a yard. Approximately how many feet is a meter?
3.
3. Okay, you don't need to know this. I mean, it's useful to know this, but you don't need to know this. There's nothing about that you have to know, okay? How many centimeters is a meter?
100.
100. A meter is the base SI unit for what? What would we be measuring with a meter?
Length.
For length. Okay, so a meter is length. Okay? A meter is precisely equivalent to a whole bunch of other stuff. Okay? A meter is precisely equivalent to one, let's do this, to 10 decimeters. You're going to want to write this down. Okay?
Also, you spelled centimeters wrong.
Oh, I forgot to say. All right. It is precisely equivalent to 100 centimeters. It's precisely equivalent to 1,000 what?
Millimeters.
Millimeters.
2 ounces.
Thank you. It is precisely equivalent to. How many micrometers is it? Precisely.
10,000.
10,000.
Yeah, that's right. Okay. That's good. How many meters would I need to get a decameter?
10.
We need 10. How many meters would I need to get 1 kilometer? Prefix kilo means
1,000.
1,000. So far, so good. Okay. What does a meter measure?
Right.
Length, right? It's a base 10 system. 1 meter equals 10 decimeters equals 100 centimeters equals 1,000 millimeters. Here's a question for you. How many millimeters do I need to get to a centimeter?
10.
It's 10. You see it there? Difference here is a factor of 10. Okay? The difference here is a factor of 10. The difference here is a factor of
1,000.
1,000.
No, 100.
No, 1,000.
Oh, yeah, that is 1,000.
Okay.
I was right the first time.
Let's do a little practice with it, okay? So I want to go from 2 centimeters, and I want to express my answer in micrometers, micrometers. So here's how I'm going to do this, okay? First of all, I'm introducing a number of different things right now, okay? I'm going to introduce some what we call dimensional analysis. Dimensional analysis is like this. I'm going to use different conversions. So I need to know how many, I'm going to multiply this by a conversion factor, okay?
That's 20.
Unless I want centimeters squared, which I don't, my conversion factor needs to put centimeters on the bottom of this equation, right? So I need centimeters down here. And what am I trying to get this into? Micrometers, right? So I believe that's like this, right? Yeah, it should be like that.
That's 20,000.
Well, hold on now. Right? Just blurting stuff up does not help us. So I need a conversion factor. How many micrometers in a centimeter? Take a look here.
1,000.
It's a factor of 1,000, right? So I can go 1 centimeter equals 1,000 micrometers.
10,000.
Hmm?
10,000.
Oh, you are right. Thank you for that. It is 10,000, not 1,000. So if I go from, actually, let's do it this other way. It'll be helpful for us, just to see more of the math. It equals 1,000 millimeters, right? And now, I need to get from millimeters to, oh, that's wrong. Let's turn this whole thing over. 2 centimeters equals how many millimeters? Well, it's 1 centimeter. How many millimeters is the conversion here? 10. Now I can get from millimeters to micrometers, and that's a difference of 1,000, right? So I can put 1 on the bottom, and I can put 1,000 on the top. And when I do this math, 10 times 2 is,
20.
say 20. 20 times 1,000 is how much? 20,000. Fair enough? Okay. If I want to take 125 millimeters and I want to know how many kilometers it is, so I take my 125 millimeters, right? Right here. What's a common factor I can get here between my millimeters and my kilometers? What are they both? What can I express them both in terms of?
1,000.
Meters, right? So, how many millimeters for 1 meter? 1,000. So, what do I put where on my equation?
You divide it by 1,000.
1,000 what?
Millimeters.
Millimeters per 1 meter. And then I multiply that, I need my meters on the bottom, right? 1 meter.
2,000.
Hmm?
2,000.
We're going to kilometers, right?
1,000.
1,000 meters
To 1 kilometer.
in 1 kilometer. Clear as mud? So if I were to start to simplify this, I get 125. My millimeters will cancel. My meters will cancel. I'm going to be left in kilometers, but I got a big old number on the bottom. 1,000 times 1,000 is?
Million.
Right? I can start moving my decimal point over. I can move it 2 over, right? Which means I can move this over. Which means I get 101.25 over 1, 1, 2, 3, 1, right?
1.25 times 10 to the.
So far, so good with me? Okay. Now, I need to get, at this point, it becomes really, really important to start converting this into scientific notation.
1.25 times 10 to the 4th power.
So I've got to move this thing over 1, 2, 3, 4 times. Okay. So 1.25 times 10 to the 1, 2, 3, 4 times, negative 10 times, or negative 4 times, right? Have you guys, are you familiar with scientific notation?
Yes.
You are. How about everybody else? Somewhat? Gentlemen?
Somewhat.
Somewhat. It's been a little bit probably, huh? Okay, well, let's get a little practice right here with this, and we'll jump back into some more of the other things. Okay. I'm going to give you a number, and I want you to write it in scientific notation, okay? Tell me how. How would I write this in scientific notation?
5.7 times 10 to the 3rd power.
You're probably not allowed to answer for a few minutes. Okay. So in scientific notation, right, generally in standard form of scientific notation, I want one number to the left of my decimal point, and only one, which means I need this to be 5.7, right? And I want to move this thing over 1, 2, 3 times, right? Now, this gets into a little bit of significant digits stuff, because at a decimal point here, I'm going to move this thing 1, 2, 3. I need to keep these zeros with me. No, I haven't gone into scientific notation or to that yet, so significant figures yet, but just hang with me, okay? I need these zeros because I had a decimal point. If I did not have a decimal point, we would ditch those zeros. It's just one of the rules of that, and I'm going to hand out a sheet to you on this in a minute. But right now, it's 5.700, and because I moved it over 1, 2, 3 times, I'm going to say times 10 to the 3rd power. What is 10 to the 3rd power? 10 times 10 is?
100.
Say 100. 100 times 10 is? 1,000. So basically, I just said, if I multiply 5.700 times 1,000, that's the same thing. These are equivalent values, right? If I multiply, get your calculator, whatever, and put in 5.700 times 1,000, do it. Don't trust me. Do it, please. Even though you know what the answer is supposed to be, just do it. Right? 5,007. It makes sense. If I multiply 5 times 1,000, I get 5,000. I multiply 5 and 7/10 times 1,000, I'll get 5,700. Right? It does make sense when we start talking about it like this. We want to have that concept down for sure. Let's do another one of these that's large like this. Okay, so I want to have 2,000 and now let's do 202. Okay, I want you to put that into scientific notation.
2.02 times 10
To
to
the
the 2nd power.
let's see. So she says, I want to do 2.02 times 10 to the, and she said the second power. So this is where my decimal is. I know that, even though it wasn't there. I'm moving over once, I'm moving over twice, therefore it's 10 to the second power. That's the same as saying 2.02 times 100. If I multiply 2 times 100, I get 200. So I mean, without even going crazy, I at least know that's a very, very reasonable answer, right? That's it. Did you guys get the same answer?
Yeah.
Okay, good, good, good. Let's do another one. Put that into scientific notation. Nah, I don't want you to yell it out. I want you to do it. Feeling good? It's okay. Even if it's wrong, it's okay. We're going to get it. Gentlemen, feel good?
Maybe, we'll see.
Okay, so in scientific notation, what do I want at the front? I want a 3 at the front, right? I want this to say 3.0, right? Times 10 to the something, right? So my something was I had to move this, I didn't move it to the left, I had to move it to the right. When I moved to the left, I had a positive value, right, for 10 to the whatever. But now that I'm moving it to the right, it's going to be a negative value, right? So I'm moving this thing 1, 2, 3 times, right? So that's 10 to the negative third. 3.0 times 10 to the negative third. Y'all feel good? That's great. Awesome. Let's do another. Do 0.395, put that into scientific notation. We should be able to do this without even thinking, right? Call it out. 3.95 times 10 to the negative 1, right? Moved it over 1 time. It's 3.95 times 10 to the negative 1. All right, let's do another one. Put that into scientific notation. What's my first value going to be? 1.2. It's got to be 1.2 times 10 to the, and then I'm just counting zeros, man, right?
-6.
1, 2, 3, 4, 5, 6. Okay? Into the negative 6. Life's good. That's real good. Okay. So we got into all this, and I can't even remember what we were doing when we started. SI units, we were talking about meters and stuff like that, right? So, all right. Let's do kilogram. Actually, let's do meters. We'll do a little dimensional analysis with meters, okay? One of the great things about the metric system is it's very precise. It's a base 10 unit. The English system is not very precise, but there's one real precise number, okay? 1 inch, by the way, this is you must know this, okay? I'm just telling you right now, you will see that this will be on a test. 1 inch equals 2.42 centimeters. Did you know that?
Yes.
Good. So now I want to know how many feet are in a kilometer. I want, and I'm going to give you that, yeah, how many feet, 1 foot, how many feet in a kilometer? Okay, we're going to work through this together. I'm starting with feet, right? So I'm going to say 1 foot. and I need a conversion factor for feet, and I'm working my way towards kilometer. What do I have that I can work with that feet? Inches. How many inches per foot? 12. So 1 foot equals 12 inches, right? That's good so far. I need a conversion factor from inches to start working my way towards kilometers, right? What can I do with an inch? 1 inch equals, or, you know, I'm gonna do this. I'm gonna keep it. This is how I was always taught to do this. One long straight line. You can also divide it into a bunch of lines. I was taught to do it like this. I don't know. However you want. What do I do with my inch? Okay. So 1 inch, and what am I putting above it as a conversion factor? 2.42
Centimeters.
centimeters. Okay. What am I going to do now?
Centimeters.
Centimeters. Okay. Per.
Kilometer.
I'm going to go meter. Let's go meter for right now. Okay. Centimeters per meter. How many centimeters do I have per meter?
100.
100. Okay. And now I can get from meters to
Kilometer.
kilometers. How many meters per kilometer?
1,000 kilometers.
1,000.
Per.
Right. 1,000 meters per kilometer. So there are a number of ways you could take this right now. The way I was always taught, the thing that makes this line very, very useful is I can multiply everything on the top and divide it by everything on the bottom. So I can go 12 times 2.42. Do that now, please. Tell me what that value is. Now, I'm going to give you one of the most useful things of your chemistry lives. Never take the first answer and run with it. Never. You may be right. Listen to me. This is all eyes up. All eyes up. It's so easy to hit something wrong on a calculator, and you mess up one thing and you messed up everything, okay? Always run your numbers for best 2 out of 3. I may run it once and I get one answer, I run it twice, I got 1 out of 2 and 1 out of 2, which one is it? And I could just be crazy and it could be some whole other thing. I'll run it a 3rd time, and now if I get that one of those numbers to repeat, I feel very good about that answer, okay? So if somebody run that number again, what do we get?
That.
Still the same thing, 29.04, good. 29.04 over
100,000.
100,000. Right? And I could like do this, I could put this into a calculator, but I could also do this. I could just say this is equal to 2.904 over
10,000.
10,000. And then I can very easily put this into scientific notation. I can say that this is equal to 2.904 times 10 to the
Negative
1, 2, 3, 4, negative 4th power, right? Shall I look at that and think about it for a minute? All right, let's work another one. I've got 5.2 decameters, and I want to know how many yards this is. Where do I begin? What's my process?
Turn meters into meters.
I got to go with 5.2, right? 5.2 dm, and I need to convert that into meters, you said. So I'm going to go dm, okay? So what's my conversion factor here?
are 10 meters in a decameter.
10 meters in a decameter. Okay, good. And what am I going to convert my meters into? Oh.
Centimeters. Centimeters.
Okay, so I'm going to convert my meters into centimeters. How many centimeters in a meter?
100
100. And now I'm going to convert my centimeters into
inches.
inches. So 1 inch equals how many centimeters?
2.42.
2.42 centimeters. And now I'm going to go from inches into
Feet.
feet.
Inches on the bottom.
Right, so I'm going to say, how many inches on the bottom?
12.
12 inches on the bottom. How many feet on top?
1.
1 foot. And now my final conversion factor is, how many feet?
3 feet.
3
1
feet
yard.
So 1 yard.
over 1 yard. Right, and so we just multiply across the top. 5.2 times 10 becomes 52. 52 times 100 equals 5200, right? Okay, that's good. I like that math. I can do it in my head. And then this bottom one is 1 times 2.42, which is, 2.42 times 12 times 3. So 2.42 times 36, right? So somebody multiply that out. Tell me what my dividend divider is here. Say it again.
87.12.
87.12, run that number again.
I got 210.83.
Let's run it again. I think that's way off.
I think so too.
I got
We're
87.12.
87.12. Just a quick look here. 12 times 3 is 36. 2 of 36 is 72 plus roughly another half. So 72 plus 18 is going to put me around like 90. So I know I'm close. This is good. Okay? And now I divide 5200 by 87.12, and I'm going to do this twice. And what's my value?
$59.687787.
Read it again.
That's what I got.
59.687787.
Did you get the same value?
Yeah.
Put this in scientific notation. What do I get?
5.9.
5.968787 times 10 to the what?
First power.
First power. Because I moved my decimal point over 1 time. Okay. The math is impeccable. That's not the right answer. You did everything right and you have the wrong answer. Because, I'm going to introduce now real quick significant figures to you. Okay. What we're going to do is, now some of these are precise numbers, like there's precisely 10 meters per 1 decimeter. Okay. So this is not limiting. This is not limiting. This is precisely 2.42 centimeters. When I say precisely, what I mean is this, okay? There are 1 inch doesn't just equal 2.42 centimeters. It equals 2.420000 on into infinity. No matter how far down I divided that thing, it's going to be exactly 2.420 forever. If I say that 1 meter equals 100 centimeters, what I mean is 1 meter equals 100.0 infinitely centimeters, okay? That's a precise number. So this is precise, 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 precise. This, not so precise, this is a measurement. We measured 5.2. The 5 was easy, the 0.2 is it's a reasonable estimate. This last figure is an estimate, okay? You ever measure something? How tall am I?
About 6. Somewhere 6'1" or 2.
6'1" or 2. Do you feel pretty good about the 6 part?
Yes.
Yeah. If I had a measuring device here, the 6 is going to be good. The 6 is going to come to about here, and then the rest of it is an estimate, right? Well, that looks like it's about 2 inches, right? Depending on who's measuring and what shoes I'm wearing, I'm somewhere around 6'2". So, first one is, we're good. We know that one. The second one is an estimate here. I don't know a third one. Well, if I don't know a third one here, I sure don't know a third one here. Therefore, I cannot go with this. I cannot go with this. I need to round this. So my 5.96 rounds and becomes 6.0, end of story. I don't get all the rest of this, okay? This is one of those details, I'm sure you've seen it in your math classes. You run into it in science. You can do all the right math and still technically get the wrong answer. If you do this, especially, if you do this on a test, I'm gonna dock you a little bit, because this is just one of those things, like, that's my job. I must, because I must get you to start thinking like this and doing this. But I'm gonna dock you a little bit. I'm not, not gonna kill you. Okay, you did everything else great, right? That's good. But we want to get to the point that we're doing this, so let's do a little bit of it. In fact, why don't this would be a good time to hand out a sheet to you. Also be a good time for some water, and I don't have any. So this is a dimensional analysis sheet. I will also have this up on Moodle. It's got some conversion factors. These are standard numbers. So you just imagine zeros going on infinitely after them. And it's asking you to, did I give you the right thing? That's dimensional analysis. I want you to have that one also. Rules for adding and subtracting significant figures. So, gives you a couple of rules here. Turn this bad boy over to where it says rules for significant figures. So we want this side here. It's got 1, 2, 3, 4, 5 bullet points up top, okay? Rule number 1 says all non-zero numbers are significant. So if I give you the number 708, all I tell you, how many significant figures are there? 3. But now if I tell you 709, well, we'll evaluate that in a minute. If I tell you 700, what if I tell you 007? What if I tell you 0.07? How do we evaluate these? Rule number 1, all non-zero numbers are significant. Okay? So this is significant. We know these two are significant. We know that's significant, and that's significant, and that's significant. What else is significant? Second rule, zeros between 2 non-zero digits are significant. So I know that this is significant. This one, and this one, and this one are all significant. I know here that all of these are significant. This next one says leading zeros are not significant. So over here, that's not significant, right? And over here, not significant. It says trailing zeros to the right of the decimal are significant. Trailing zeros in a whole number with the decimal shown are significant. So right now I've got 700. Okay? I could also write this like this, 700 point. I could also write this like this, 700.00. Okay? So let's try to make sense of these rules. Trailing zeros to the right of the decimal are significant. Well, here I don't have any decimal. How do I know if that's significant? Here I have a decimal. I don't have anything to the right of it. Here I've got a decimal and I've got 2 zeros to the right of it. They're significant. Any numbers between significant numbers are significant. So I know that whole thing is. We still have, and we know that is, right? And we know those aren't. We know that is. We know those aren't. But what do we do about these? Well, let's move down here. It's got some some more explanations. Number one, it says all non-zero numbers are significant. Number 33.2 has 3 significant figures because all of the digits present are non-zero. So if I have 33.2, all of them are significant. Number 2 here, zeros between non-zero digits are always significant. It gives you the number 2051, right? Zeros between other significant digits are always significant. It says here, leading zeros are not significant. They're nothing more than placeholders. The number 0.54 has only 2 significant figures. 0.0032 also has 2 significant figures. I could rewrite this, couldn't I? How would I rewrite this in scientific notation? 3.2 times
10 to the third.
to the
Negative.
1, 2, 3, negative third, right? Whatever my significant figures are here, I need to have them represented that way here also, okay? This next one says, trailing zeros in a whole number with the decimal shown are significant. Placing a decimal at the end of the number is usually not done, by convention, however, this decimal indicates a significant zero. For example, 540 decimal point indicates that the trailing zero is significant. There are 3 significant figures in this value. So I wrote 700. We're still having a question mark here, but because I have the decimal point here,
Yes.
I know that these are all significant. Now let's go to number 6. Trailing zeros in a whole number with no decimal shown are not significant. Just writing 540 indicates that the number 0 is not significant. So significant figures do I have here?
1.
1. These are functioning as placeholders. I would take that, how would I write that in scientific notation?
7 times 10.
7 times 10 to the,
Second power.
7 times 10 to the 1, 2, right? To the second power. We'd have no problem with that. Trailing, we just did that one, didn't we? Without,
Yeah.
trailing zeros without, okay, number 7, exact numbers have an infinite number of significant figures. We talked about that, right? 2.42 centimeters per inch is 2.42000 infinitum. And number 8, for a number in scientific n times 10 to the x, all digits comprising the n are significant by the first 6 rules. So we'll get into that. Let me erase a little something here, okay? Okay, we're going to work backwards and forwards. How many significant figures does this have?
5.
He says 5. Which rule tells me that I have 5?
Zeros to the right of the decimal.
Zeros to the right are always significant. What this is telling me is basically somebody measured this joker and there was a 0 there. They looked at it and there's a 0 there. If they didn't look at that one, they wouldn't have that one. And now they're telling me, okay, I have 4 because they measured that one and it came out as 0. This could just as easily, because this last one's a guess, they could just as easily have guessed 1 and we go, oh, that's a significant figure. They looked at that. Okay? What if they had just that? How many significant figures do I have?
3.
3.
What's the rule?
All
All non-zero numbers. Good. What if I had this?
Still 3.
So 3, because that last 0 is just a placeholder, right? How can I turn this 3 into a 4?
Add a decimal.
Add a decimal point. That's all I have to do. So far, so good? Okay. And let's do this. How many significant figures in the first one?
3,
Second,
2,
third one,
7.
7.
7. Okay. How many significant figures?
2. 2, 4, 4.
In this case, it's just 2. What would this look like, by the way? It would look like 7, 4, 0, 0, right? My rule would say these don't have a decimal behind them, so they're insignificant, right? It only have these 2. How many significant figures or digits here?
4.
4. How many here?
4.
Why 4?
Because 0.
Why not 1?
They're to the right.
They're to the right, right? Good. How about here?
4.
4, right? All non-zeros and the zeros in between are significant. Well, that's good. Okay, here's what I want you to do real quick. Where are we on time? I think I don't have time for what I want to do. Oh my goodness, I'm down to 20 minutes. Okay. All right. I don't think we do have time for that. Let's take a look at some dimensional analysis. Okay. We've done a bit of it. I'd like us to do a little bit of more. You have this dimensional analysis sheet. Pick a random number, 1 through 10, go. Ingrid.
7.
7.
7, that works. Okay, we're doing number 7. Convert 27 kilometers per hour into meters per second. I need to get to meters per second. What has to be on top?
Meters.
Meters must be on top. What needs to be on bottom?
Second.
Seconds need to be on bottom, right? So I've got to multiply this by a conversion factor. I can take 1 hour
60 seconds.
and I can put it into,
60.
let's go minutes, right? 60 minutes. And I can take my 60 minutes and I can convert it into seconds. So 1 minute equals
60 seconds.
60 seconds. Good. And now I can start working on my kilometers. I want to get this into what?
Meters.
Meters. So I need meters on top, right? So I need kilometers on bottom. So 1 kilometer equals
1,000 meters.
1,000 meters. Right? Let's make sure that our units cancel. I have kilometers here. I have kilometers here. I have hours here. I have hours here. I have minutes here. I have minutes here. That leaves me with meters per second. We do the math, right? And got like 27,000 meters over 360 seconds, right? You guys do me a favor and will you run the math on that?
75.
75, he says. That's what you get.
Yeah.
Give me the whole, like
That's it.
works out perfectly?
Yeah.
Oh, wow. Okay. Do me a favor, somebody else run that math. We're not trusting this guy. Jace, you got it? You don't have a
Yeah,
calculator.
it's 75.
Huh?
It's 75.
75, okay. Is this the right answer?
Yes.
Yes.
When I ask you that, what am I really asking you? Does it have the right number of significant digits and or figures? So since this was 27, no decimal point, right? And nothing after it, it's exactly 27. I need 2 in my answer, and that's what I have, right? So that worked out beautifully. Let's try another one of these, okay? Jace, you want to pick a number for us? Not 7?
Let's do,
Don't look at it.
let's do number 2.
Number 2, all right. What does number 2 say? Convert 32 years into hours. Okay. You guys don't need me for this,
Okay. That's funny.
right? It's a big old number, isn't it?
Yeah.
Let me do this. Let me do this. Hey, guys, let me do this. Change this up on you. 32.00 years. I'll be right back. Y'all solve this.
There we go. You got an answer? Yeah.
What'd you get?
2.800 times 10 to the 5th power.
Did you get the same?
I-
Not there yet? Okay. I'm gonna start working it while y'all are doing that, okay? What am I trying to get into?
Years. Hours.
Hours.
So that's days,
Okay, hold on,
365
hold
days.
on. Hold on. Trying to get into what? Hours?
Hours.
Okay, that's not bad.
What? That's
That's it, right?
That's what I got.
Did you do this?
0.25.
Yeah, why did I do that?
Why did you do that?
Oh,
Why did I do
leap
that?
year.
Leap year, right?
Let's see if I do the same.
You get a leap year every 4 years, right? So it's each year's really, if we're looking for the total number of hours on average, it's 300, or number of days in a year, it's really 365 and a quarter. So this is nice. I don't have to do any division, right? Give me this big old long number. Tell me what this number is. Not in scientific notation. Not with proper sig figs.
8,766.
That's it.
I got 280,512.
280,512. Exactly. Run that number again. Somebody give me the same number. Okay.
Got the same thing.
You got the same number. Good. Why do we do that? Why do I make you run them twice?
Make sure they're right.
Make sure it's right. If you get the same number twice, we can roll with it.
So it's actually-
Trust me, it stinks. You do this big old problem later on in this class, and you just happen to hit a wrong key and you miss the whole, a bunch of points on the test because of it. That
So
just stinks.
It's actually 2.801 in
Okay, so-
scientific power.
Yeah, let's go ahead and put this into scientific notation. I'm gonna get, I got a decimal out here, right? So I'm gonna go 1, 2, 3, 4, 5. So what's my answer? 2 point what?
8.
Oh,
8, 0, 5, 1, 2 times 10 to the what? 5?
5.
10 to the 5th. And now I need to put in the proper number of significant figures. So I've got 1, 2, 3, 4. So I'm going to go 1, 2, 3, 4. I'm going to get rid of
1 and 2.
1 and a 2. All right. And there you go. That wasn't so bad, right? Okay. How much time do I have? I got 10 minutes. That's not much.
Wait, why'd you do 4 again?
Oh, because I began with 4 here.
Okay. So you gotta have 4 over here.
So I'm going to have 4 over there.
Okay.
Yeah. Good question. This is going to look like a joke now that we've done all this. But be fair, take a look at this one that says rules for adding and subtracting significant figures. It's got 2 columns on it. Take a look at number 10. How many significant figures in number 10?
4.
4. How many in number 13?
2.
How many in number 9?
3.
Number 9?
2.
Oh, number 9 is 3. I'm sorry. I meant 19.
2.
2. How many in number 7?
5.
Okay, now, let's look at this. So it says rules for adding and subtracting significant figures. Count the significant figures. Count the number of significant figures in the decimal portion of each number in the problem. Then add or subtract the numbers as you normally would. Then round the answer. So we do our rounding and everything else at the end on adding and subtracting. So let's look at one of these that adds and subtracts. Let's do number 21 on here. So number 21 says 6 plus 11.2. Well, that answer in your head just becomes 17.2, but when I use the proper number of significant figures, what does this become?
200. No, 220.
So I have 17.2, right? I can only have one significant figure because I just had this 6 over here.
So 20.
So this 2 is a goner, right? It rounds down to a 0, right? So now I'm dealing with 17. I got to get rid of the 7 because it's too many significant figures. Am I rounding up or down?
Up.
I'm going to round up, so this becomes 20. So 20 would be the correct answer for number 21. Write that in if you would. Let's go ahead and let's do number 29. Number 29 says 800 plus 2.
That's just 800.
Of course, that would become 802.
No, I mean the mid significant.
I know it, which is just going to become 800. And if I wanted to write this in scientific notation, I'd write this as,
8 times 10.
shh, you hush for a second. I need some, yes ma'am.
Is it only 800 because of 2, you round it down?
Because the 2 only has one significant figure. Okay, so what I'm doing when I'm adding these, adding, multiplying, dividing, comparing, whatever. I'm always worried about what's the smallest number of significant figures I have, and that is my limiting factor. This has how many significant figures? Digits?
1.
This one has 1, okay? Because this is significant and these are not. This one has 1, right? So I can only have one significant figure in my answer. Let's try this a slightly different way, okay? What if I had How many significant figures here?
2.
2, right? How many here?
3.
3. If I do this math real quick, this is gonna want to be 882, but I can only have how many significant, I gotta go with the lower number, right?
2.
So I gotta go with that. So I can't have 882, I've got to have 880. Okay? Let's try another one real quick. Let's do 0.0001 plus 343.0001. How many significant figures do I have here?
4.
1.
1. How many do I have here? 1, 2,
7.
3, 4, 5, 6, 7, right? But let's go back and read our rules. Let's make sure that we got this right. So it says, count significant figures, count the number of significant figures in the decimal portion of each number in the problem. So maybe I messed this, it's entirely possible we messed this up. We're looking for the decimal portion. How many do I have here?
1.
1. How many do I have here?
7.
No, in the decimal portion.
No, 4.
4, okay? Don't let me mess you up, because I could. Add or subtract the numbers as you normally would, then round the answer to the least number of places in the decimal portion. I didn't say that right last time, right? So, of course, this one would have how many in the decimal?
0.
0, and this one would have 0, so 802 would be my answer. Yeah. I may have just blundered. It is entirely possible. I will come back and check on that. Let's do some multiplication, okay?
Oh no, it clarifies at the bottom. It means the whole answer. It means the whole question.
Let's do number 24. So number 24 here says 5.0 times 6.2. How many significant digits do I have here?
2.
2. How many do I have here?
2.
2. Okay, so how many will my answer have?
2.
2. So you do the math. What do you get? 37 or something like that?
31.
31, sorry. Did too many. Okay. So 5.0 times 6.2 equals
31.
31, right? Okay. Let's do number 27. 5,000 divided by 45.2. How many significant figures here?
1.
1. How many here?
3.
3. How many will be in my final answer?
1.
1. Okay. So go ahead and do this math. What do you get? Give me the long number. Don't worry about rounding yet.
110.61.
110.61. Can somebody verify that?
949.
9469.
Yeah, after.
Okay,
everybody's got that?
Yeah.
Okay. How many significant figures am I allowed to have?
1.
1, right? So I do my rounding, that becomes a 7, that becomes a 5, that becomes a 0, that becomes a 1, that's 6, becomes a 0, that becomes a 1, I got 111, blah, right? But I'm only allowed to keep this one, right? So my answer would be
100.
100. What's this in scientific notation?
1 times 10 to the second power.
Good. What's this in scientific notation?
3.1 times 10 to the first power.
Okay. So it's 100. Questions? Okay. You need to try to catch, it's not complicated. I'm just letting you know right now, you're responsible to know the SI units for time. What is it? Okay, second, right? It's going to be on your notes here. I handed them out to you. So SI units for time. Time's on there, isn't it? It's seconds, yes. For length, it is meter. For mass, it is
Grams.
Kilograms.
yeah. And for temperature, Kelvin. And we didn't work any temperature problems, did we?
No.
Oh, I wish we'd worked some temperature problems. We're out of time, aren't we?
Yeah, we're out of time.
So y'all are supposed to have a lap, right? Can I take just a little bit of lap time and do a couple temperature problems? Okay, cool. Let's do that. All right. This will be well worth it. You'll be glad.
You didn't give us the temperature on the sheet, though.
It's in my head. Okay. 2 things you've got to know for temperature, okay? It's 2 degrees Celsius. It's kind of the common denominator. Degrees Celsius has a range in water of 0 to 100, right? Water freezes at 0. It boils at 100 at standard temperature and pressure, which, by the way, that means like we're at the ocean side, and so air pressure is standard. Okay, so 0 degrees or degrees Celsius. I can convert that into Kelvin. Anybody ever heard of Kelvin?
Yes.
Okay, what is Kelvin?
It deals with absolute zero.
Yeah, Kelvin is the temperature, the hypothetical, I'm going to say, temperature of absolute 0. That's the temperature at which there's no energy. It's the temperature of 0 energy, so nothing is moving anywhere, okay?
Negative 212.2 degrees
No,
Celsius.
negative 273.15
Oh, I was wrong.
degrees Celsius. So if I want to get from Celsius to Kelvin, I subtract 273.15. Okay? If I want to get from Kelvin to Celsius, I add 273.15. What temperature in Celsius is absolute 0?
Negative 273.15.
Negative 273.15. What temperature in Kelvin is absolute 0? 0 degrees. Okay? Let's do a practice run. So I want to know what temperature Kelvin does water boil? Shouldn't even need a calculator.
273.15.
Nope.
Wait, you said
I want to know what temperature. I want boiling point of water in degrees Kelvin.
yeah, I'm right.
What did
273.15. Yeah, it would be 0 degrees Celsius.
Yeah, that's not the boiling point. That's the freezing point.
Oh, okay. So,
Okay, so I got
373.15.
I got 100 degrees Celsius, right?
I just said freezing point.
And now to go from Celsius to Kelvin, what do? Subtract 273. And I will get 100 minus 273 equals. Am I going backwards?
Yeah, you go backwards.
I'm going backwards. We're going to add. Just set my, y'all ever go into a loop in your head? Okay. We're going to add 273.15 to my Celsius, and what am I going to get? For my Kelvin? 373.15.
You forgot to break.
Thank you, sir. Don't worry, it'll get better in time. All right, let's do, let's do 52.4 degrees Celsius into Kelvin. What do I do?
And 300.
Add 300,
I mean 270.
add 273.15. What am I gonna get?
325.55.
So let me check his math.
And I did that.
Will there be a time
Yeah.
when you subtract it?
Yeah, if I'm going the opposite direction.
So if you're going from Kelvin to Celsius?
Yes. Okay, if I've got 10 degrees Kelvin and I want it in Celsius, what's that going to be? 10 minus 273.15 becomes?
263.15.
Yeah. Negative 263.15 degrees Celsius. So that's not bad, right? All right, now, we feel good about Kelvin and Celsius so far?
Yeah.
Okay. You do need to know Kelvin because we'll use it a lot, an awful lot. It comes into a lot of formulas and constants. Okay, let's do Fahrenheit. This is another system you need to know, okay? There are two ways of looking at this. Or divide 9 by 5 and you'll get 1.8. Some people like to use the 9/5. Some people like to use the 1.8. I just always did the 1.8. Freaks me out when people use 9/5, but you can do whichever one works for you. Okay?
Down to 9/5.
People like fractions. But at any rate, if I have, let's test this, okay? If I have 0 degrees Celsius, I want that in Kelvin, right? So I'm going to do this to it, right? I'm going to multiply it by 1.8.
You mean Fahrenheit?
I want it in Fahrenheit, I'm sorry, thank you. I'm going to multiply my degrees Celsius, 0 degrees Celsius times 1.8. What's that, by the way?
0.
0, and I'm going to add 32 to it, and what do I get?
32.
32, and is that the temperature water freezes at in Fahrenheit?
Yes.
Yeah. Let's do another one. Let's do 100 degrees. 100 degrees centigrade. I multiply that times 1.8. What do I get?
180.
I get 180. I add 32 to it, and what do I get?
212.
Is that the temperature that water boils at in Fahrenheit?
Yes.
Yeah.
It's 212, not
Oh,
112.
sorry, what did I say? So far, so good? Okay. All right. Now, if I have 48.79 degrees Fahrenheit, and I want to convert this to Celsius.
So minus.
Remember, my formula here was Fahrenheit equals degrees Celsius times 1.8, and that whole thing plus 32. If if we just do order operations and try to solve for Celsius, then I go F minus 32, right? Divided by 1.8. So I got to do that. By the way, this 32 is a perfect number. 32.0000 infinitum. So I'm gonna go 48.79. What am I gonna do? Not Matthew right now. Somebody else, what do I do?
Subtract 32.
Subtract 32. And what do I do with this? Divide by 1.8, and I will get,
9.327777, and just infinite.
okay, too much. You have too many in?
9.327 infinite.
Okay. All right. And of course, how many significant figures can I have here?
Infinite.
No,
You said that was.
I can have 4.
Oh, yeah.
1, 2, 3, 4. So I'm going to go, actually, this is perfect, just like that, 327. Let's do 2 more, and I'll cut you loose. And don't forget, you've got that quiz. Please do that. It's going to help you. We're going to be rolling on to atoms next week. All right? So, actually, Wednesday. Roll on. It's happening fast. Here we go. Let's do 458 degrees Kelvin. I want this to Fahrenheit. Right? So, how do I get from Kelvin to Celsius?
Subtract 273.15.
I'm going to go 0, 0 on this, okay?
Okay.
So bad. I'm going to subtract 273.15. Okay? And then what am I going to do? That's going to put me in Celsius. Then what do I need to do?
Celsius, Fahrenheit.
How do I get from Celsius to Fahrenheit?
F minus 32 divided by 1.8.
Okay, how do I go from Celsius to Fahrenheit?
Times 1.8.
Times 1.8 times 1.8 plus 32, right? So
364.73.
364.73. So we check that math.
Yeah.
Okay. Do I have the right number of significant digits here?
Yes.
All right, how many do I have up here?
5.
1, 2, 3, 4, 5. Here I have 1, 2, 3, 4, 5. That's great. Okay, one last one. .32 degrees Fahrenheit. I want this in Kelvin. It's my order of operations. So what do I do here? What do I do? First thing I do from this. I gotta get from Fahrenheit to what? To Celsius. What's the first thing I do then?
Minus subtract 32.
Subtract 32, right? And then what am I going to do with this?
Divided by 1.8.
Divide it by 1.8. And then what am I going to do now? If I go to Fahrenheit, or to Kelvin.
Add 273.15.
Add or subtract?
So it is
Subtract.
271.1.
Well, everybody run that number for yourselves?
Going from Celsius to Kelvin.
Yes. In this case, we're going from Fahrenheit to Kelvin.
271.1. And that is adding 273.15 back, subtracting.
It should be added. That's right. And you don't miss that we're going to add 273.15, not subtract. Okay. Just a quick thought for that is that 0 degrees Kelvin equals 273 degrees